This comes out of section 8.6, logarithmic differentiation. Make derivatives, some derivatives, quite a bit easier. Say, for example, we're given something extremely kind of onerous here, where we've got all kinds of stuff going on, and so if we were asked to differentiate this in the early parts of the course, as soon as we got the ability to do chain rule, product rule, quotient rule, and then to know what the derivative of e to the x is, we could do this question, but it would be a bit nasty, right? We'd have to say, oh well, our derivative is the bottom times the derivative of the top, which needs product rule to say e to the x times 1/2 x cubed minus 7 to the negative 1/2 times 3x squared, and then plus e to the x times the square root of x cubed minus 7, and then minus the top, so e to the x square root of x cubed minus 7 times the derivative of the bottom. Now I'm already running out of space, but you can see where I'd have to have now 4 times x squared plus 5 to the 3 times 2x. All that's the numerator, and then the bottom I have to do the bottom squared for the part of the quotient rule, and I end up with something like that. Now, could that be simplified further? Definitely, but I mean, if I was asked what's the slope of the tangent line when x equals 10, I could put in a 10 here and see what crazy number this is going to give me. The question is made much easier if I try taking the natural log, the log of both sides. So now, if y equals this big thing, then the natural log of y should equal the natural log of this big thing. Now, at first, that looks like I've just made it more complicated. But let's take a look at how nicely the log rules will actually pull apart that huge complicated function to say, well, that means then I've got ln of e to the x plus ln of the square root of x cubed minus 7 minus ln of x squared plus 5 to the 4th. So ln of y equals, ln of e to the x is just x. Anything with an exponent on it, we could bring the exponent outside. So for example, this natural log of x cubed minus 7. And the same thing here, I could bring this 4 out front, say I have 4 times natural log of x squared plus 5. Now it turns out that the derivative of each one of those terms is not very complicated. Like if I take the derivative of everything with respect to x, so in other words I basically do implicit differentiation here, I'm going to have, well, the derivative of y is 1 over y times y prime equals, now the derivative of x is 1 plus 1/2 times 1 over x cubed minus 7 times the derivative of x cubed minus 7 minus 4 times 1 over x squared plus 5 times the derivative of x squared plus 5. And if I want y prime all by itself, I just have to multiply the whole thing by y. So I'd have y times 1 plus, and I could make this look a little bit neater and tidier, but basically 3x squared over 2 times x cubed minus 7, and then minus 8x over x squared plus 5. Now, if you prefer not to have a y, like if they say find the derivative with respect to x and want it in terms of x, I just have to go back to the beginning and say what y was. So my derivative is the initial function I was given times the stuff that I have in the brackets here. Now, it's not necessarily a short process, but definitely, hopefully, you can see the value in how much less difficult the algebra work it was to get to this expression for the derivative than it would have been, or than it was to get to the one up above where I had to use product rule, chain rule, quotient rule, and all those things. This just requires me to know log rules and be able to pull this thing apart. And with the same final result, that if I was given a number like x equals 10 and they said what's the slope of the tangent line, I could put 10 into this and come up with an answer just as well as I could have up above. In fact, probably a little bit easier than I could have up above. Last thing I should mention is you can't log a negative number, which in some some functions is a big deal. You have to deal with that differently. In this case, if you look at the original function, I intentionally chose something that didn't have any negative number possibilities, and e to the x is always positive, the square root of something is always positive, and anything to the fourth power is always positive. So all the separate components of y equals are all positive, so taking the log of any of them was going to be fine. Even if that wasn't the case, I'll show you in the next example how you can get around that anyway.